From what we have just learned from previous discussions, we know that electric current will flow if these two requirements are met. These requirements are, first, there should be a closed loop, and this loop should be conducting loop, and there should be a push or a potential difference to make the charges flow. And where will this potential difference come from? It will come from the battery. Okay, and now when electric current is already flowing in a closed loop after the charges have been pushed by a battery, we now have an electric circuit. Okay, and then when we when we say that the electric circuit is closed, current is flowing. That means charges are moving around the circuit, and current can actually be measured. It's a physical quantity that can be measured. Current, we represent current with capital letter I, and this current means this is amount of charge flowing in a specific cross-sectional area of a wire per unit time. Okay, so let's assign the symbol for current as I. What will we use for charge? Maybe let's use Q and then time for T. Okay, so in formula, we know that current is the number of charge that flows through a cross-sectional area of a wire per unit time. And for the SI units, SI unit for current is ampere or capital letter A. SI unit for charge is coulomb, capital letter C. And SI unit for time is second or S. Okay, so going back, current is the number of charge flowing through a cross-sectional area of a wire per unit time. So for example, we have 1 ampere of current. That means 1 coulomb of charge passes through a cross-sectional area of a wire per second. Okay, so that's what current means. And then we should also take note that this 1 coulomb of charge does not mean one piece of charge only. It can mean a lot of charges. Remember, what's the charge of an electron? Remember, the charge of an electron is negative 1.6 times 10 raised to negative 19 coulomb. So imagine, for 1 coulomb, how much electrons does 1 coulomb of charge contain? Okay, so we are going to consider this in terms of coulombs, not just only one piece of charge. Okay, now let's discuss the conventional current direction. Now, for discussion purposes, I'm using this picture or diagram to represent a battery or a cell. But remember, the symbol for cell or battery is this. This is the symbol for a cell. The long one represents the positive terminal and the short one represents the negative terminal. So don't get used to Miss Abby's diagram. This is only for discussion purposes. And always remember, if we're talking about flow of electric current flows from the positive terminal of the battery or cell going to the negative terminal. That's the direction of our conventional current. Again, we are referring to conventions. This has been established already for many years, so this is what we are using right now. Okay, let us now try to imagine how charges flow around a circuit when the circuit is closed. Remember when you turn on, for example, the switches here, when you turn on the circuit, almost immediately the lamp will light up. And then when you turn it off, the lamp will immediately turn off. Now what happens? It's important to note that charges do not move very fast. They actually move very slow. But why is it when we close the circuit, the lamp immediately turns on? Because it's like this. You can imagine the charges like they are falling in line. They are in queue to wait for their turn to light up the lamp. So that when we switch off, when we close the circuit, the battery will push out a charge that already carries an energy. So imagine the battery push this charge. What will this charge do to this one? They will push this one will push this, pushing, and you can imagine the domino effect until one of this that's next to the lamp moves to the lamp and the lamp lights on. It works. So please take note again, it doesn't happen this way. Turn on the switch and then the charge goes out of the battery and then zoom. No, it's not like that. And also, just imagine that charges flow very slowly, but why? But we can light this up immediately because the charges are in queue. They are pushing each other every time the battery pushes on the new charge that comes out filled with new energy. For example, let's zoom in this. Remember, I'm referring this to one coulomb of charge, meaning it can be composed of a lot of tiny charges. For example, let's zoom into this wire. What happens inside the wire? Inside the wire, a charge carrier moves very slowly in a zigzag random way. So sometimes when it takes 2 steps forward, that will be equivalent to a 1 step backward, and along the way it will meet some other barriers like another atom that can be there. So that's how it moves, each charge. Okay, but the charges just push on each other, waiting for their turn to light up the bulb or any device that we have here to make it work.